Okay, so reviewing how the continuity test is going to work when x is negative 2. When x is negative 2, we start by taking negative 2 and plugging into the function to first see if we even have a value defined for that function at negative 2. So we plug into the piece where x would be negative 2. That would be this second piece because of the equals 2 aspect there on the inequality. So when we plug into x squared minus 2, we've got negative 2 squared minus 2 if I write out the substitution, and that's 4 minus 2, so I get 2 back. We know f of negative 2 now is defined. The next part we considered in a continuity test revolved around the limit. So we looked at the limit as x approaches negative 2 from the left. We looked at the limit as x approached negative 2 from the right. And the goal here was to sync up the right pieces with the left-hand side and the right-hand side. So with the left-hand side, we're talking about values that are less than negative 2, so I use this first piece here for my left-hand limit. From the right-hand side, I'm taking everything greater than negative 2, so I come back to the second piece, use that for the right-hand side. Once we line up our pieces, then we just take what x is approaching here of negative 2 and we plug in. So when I plug in here, I've got 3 times negative 2 plus 1, that's negative 6 plus 1, that's negative 5. And then when I plug in here, we already know what happens. We get 2 back. So left-hand limit does not match the right-hand limit, meaning the limit as x approaches negative 2 applied to this function does not exist. And when the limit does not exist, we can draw the conclusion that the function is not continuous at x equals negative 2 because that limit does not exist. So as long as we're reviewing continuity tests here, eventually we'll get to the differentiability side. Let's focus our continuity test attention here on x equals 1. So when x equals 1, we start the same way. We're going to take 1, we're going to plug into the function where 1 is defined for x, and 1 is defined for x right here with the second piece because x is less than or equal to 1 there. So we plug into x squared minus 1. 1 squared, or sorry, not x squared minus 1, minus 2. 1 squared minus 2, which gives us negative 1. And then looking at the left-hand limits and the right-hand limits here, limit as x approaches 1 from the left, limit as x approaches 1 from the right. Once again, looking at the left side, we're looking at values that are less than 1, so that's going to go back to this second piece right here. Left-hand limit will be applied to x squared minus 2. And from the right side, that's going to be where it's greater than 1, so we'll look at this last piece here of 3x minus 4. Analyze that from the right side. So we set up our pieces, take what x is approaching, in this case 1, plug in. We already know what happens on this first piece. We know we're going to get negative 1 back. Turns out for the second piece, you got 3 times 1 minus 4, also negative 1, so same value back, meaning that limit does exist. So the limit as x approaches 1 applied to this function, since the left-hand limit and the right-hand limit both gave me negative 1, that equals negative 1. So our function, turns out here our function is continuous. It's continuous at x equals 1. And it's continuous because, it's not just because the limit exists and the limit is negative 1, but it also is because f of 1 is negative 1, right? These two values here have to match up. So the limit as x approaches 1 applied to our function is equal to, well, basically the original step. F of 1. So one side it's not continuous, the other side it is. Where this whole differentiability concept comes in. Well, we have to take all this continuity stuff, use this as background to now transition to the differentiability side. If I were to analyze a differentiability test, let's say, at that first value in question of x equals -2 that we looked at, as far as being all formal here is concerned, the good news is I don't really have any work I have to do. Because if a function is going to be differentiable, remember it has to be continuous. So since we found it was not continuous at x equals -2, we just slap a little therefore statement on this and say f is not differentiable at x equals -2 because f is not continuous at x equals -2. It's a pretty easy test to conduct on the differentiability side when you already know it's not continuous. Now, when it is continuous, and you have to consider the differentiability test for that other value in question, which was x equals 1. Okay, here you have to take it just a tiny step further to draw your conclusion. And what we're going to do, because differentiability revolves around the idea of taking a derivative in the first place, is we're going to go back to the original function and we're going to take the derivative of it so we can use it. Now, we haven't done this before where we take a derivative of a piecewise function, but it's not too hard. All you do is you take a derivative of each respective piece. So we started with 3 pieces on the function. We'll have 3 pieces on the derivative. If I take the derivative of the first piece, 3x plus 1, that's just going to be 3. And the domain is still going to be for all x values less than -2. Take the derivative of the second piece, got x squared minus 2 over here, so that's going to be 2x over here. If -2 is less than or equal to x is less than or equal to 1. And then looking at that last piece, derivative there is 3. So it would be 3 if x is greater than 1. So how we use this now for a differentiability test. Remember, we're looking at the differentiability test as we're considering x equals 1 here. So we're going to focus our attention in on the 2 pieces where x revolves around 1. That means we basically take this guy out. We don't need it for this differentiability test. We just need to explore what's happening with the 2x and the 3. So if I come back over here, this is what I want to know. I want to know what the value of the derivative is at 1 as I explore this from the left. And I also want to know what the value of the derivative is at 1 as I explore it from the right. So, kind of similar to what we were doing with left-hand limit and right-hand limit stuff. You know, I go back. I want to look at the left side here. I'm looking at values for 1 that are less than 1, so I use that second piece, that 2x. If it's 2x for this particular part that I'm applying, and I know x is going to be 1, take 1, plug in. From the left, it's going to be 2 for this derivative. And then from the right, exploring here values at x is 1. From the right, those values would have to be greater than 1. So I'm taking that last piece. That last piece is just a 3, so no matter what x is, I'm plugging in, I get 3 back. What happens here is I get 2 different values. So once again, kind of connecting the limits, right? If it's limits, that stuff doesn't exist. Here, derivative doesn't exist. So the conclusion we draw is f is not differentiable at x equals 1 because f prime of 1 does not exist. And the reason it does not exist is because of what we just showed up here. F prime of 1 from the left does not equal f prime of 1 from the right. Try to figure out a and b knowing this is continuous and it's differentiable. Let's start, because we know we're going to have to use it, let's start by taking the derivative of the function. So f prime of x equals, I'm starting with two pieces for the original function, so I'll have two pieces for the derivative. When I take the derivative of the first piece, pretty simple power rule here, it's just going to be 12x cubed minus 12x squared minus 24x, and then 5 goes to 0. Domain restriction, that stays the same, so x is greater than or equal to 1 for that piece. Now, understanding we're trying to figure out what a and b are, so a and b are actual numbers. When I take my derivative here, a and b are just coefficients to start. If I do a power rule on ax squared, I'm bringing 2 down, I'm multiplying to a, so that's 2a. And then the new power will be 1, so it's 2ax. Then I got this plus bx. Well, rule is if this is just an x, you drop it and you keep the coefficient, so drop it, keep the coefficient of plus b. So that'll be the second piece if x is less than 1. Okay, we're trying to find two variables, so it makes sense to try to set up two equations. Use maybe some substitution, some elimination, if you're a little more daring Kramer's rule, to figure out what a and b are. So I'm going to go back to the original function now. If this is going to be differentiable, it means it's going to be continuous. So these two pieces have to meet at the same point. That point would be where x is 1. So take 1, plug in for x here. If I plug in for x here, it's 1 to the 4th, 1 cubed, 1 squared, right? It's going to be 1 for all those. Multiply these coefficients, so you're just going to have 3 minus 4 minus 12 plus 5. So I took 1, I plugged in up here. I'm going to set that equal to, take 1, plug into the second piece. So plugging in the second piece, knowing x is 1, we just get a plus b back. So trying to form two equations so I can solve for a and b. Looks like I got one equation now. I got a plus b equals, do my simple calculation over here, negative 8. So that's kind of with respect to the continuity side. Now, what we would consider to be, the differentiable side, we try to match up pieces here on our derivative, knowing this idea is coming together where x is 1. So in a similar fashion, I start with this first piece, I take 1, I plug in for the x's. Well, if I plug in for the x's, I get 12 minus 24, which of course will give me negative 24. Now I need to set that equal to the second piece when I take 1 and I plug in for x. There's only one x to plug into here. If that's 1, I'm going to have 2a plus b. So this 2a plus b equals negative 24. Trying to find two variables, need two equations. I've got two equations. So set these two equations, well, maybe stack them on top of each other. If you stack them on top of each other, you could see that elimination could be a good way to go here. Because with what I'm seeing, these b's would go away pretty easy if I took one of these equations and multiplied by a negative 1. So maybe I'll multiply the second equation by a negative 1. Just changes all those signs. So now if I add through, I've got 16 here. Got negative a there, b's subtract out. So negative a equals 16 means a equals negative 16. Objective is to find a and b. You got a. As far as b is concerned, well, go back to one of these two equations and plug in to figure out b. If I take negative 16, I plug in right here, I'd be adding that over here. So b is going to be, looks like b is just going to be 8, right?